optimization.
Thank you. Thank you. Is that working? Okay. Yeah. So we had I think on Tuesday, was it that was your talk on Tuesday, Jonas? Yeah. So we had already like at least one glimpse in symmetry reduction. And we talked about minimizer extraction, then the moment SOS hierarchy context. And today I want to talk more about sort of the algorithmic side of how to actually obtain symmetry reductions and how to do it kind of fast, because things don't scale that well. Yeah, okay. Okay, so first I want to talk a little bit about sort of the theoretical setup. It's not going to be very deep. And then I will go into one specific case where I know so symmetry reduction is very fast, and I implemented this, and then I will explain sort of what the purpose of this project is going to be and how it's going to evolve, because I want to sort of take all the cases in which it works well and sort of put them in one package and then have it ready for use. So we are in a setting where we have a finite group. We just take it as a subgroup of the unitary matrices, and we take the linear action on Cn. And this induces an action on the polynomial ring. We always wanted like a finite dimension representation, so we just truncate the polynomial ring. And then we also have the invariant ring, which is just all of the polynomials up to degree d, which are left invariant under this induced action. In particular, we have the Reynolds operator, which is exactly the projector from your polynomial ring onto the invariant ring, which you just get by averaging over the whole group. So you take any polynomial, average over the whole group, and you end up in the invariant ring. And the next object that will be very interesting for us is the commutant, which is the set of all linear maps that are equivariant under the action of G. And so we have basically two computational tasks here that we kind of have to be very careful about, because everything explodes all the time. And the first one is we need to be able to evaluate the Reynolds operator efficiently. If you think about, for instance, a permutation action, just a pure permutation action, then what evaluating the Reynolds operator on a monomial would mean is you just construct the orbit sum. So you start from one monomial, you apply the action over and over again, and you end up with a sort of whole sum over the whole orbit. And this would be very important for us to find a good basis sort of to start with in the moment S2S sense, or S2S hierarchies. And we also will need like a basis of the invariant ring. And then the second big task is we need to block diagonalize the commutant. And we can do that in such a way that sort of we can do this as finely as representation theory allows. And this is computationally also pretty hard task. And then the applications are, for me, the main application is in semi-definite programming, and in particular, those programs that come from moment SOS. Okay. Now I will tell you a little bit about sort of what is already there right now. And so there's, for instance, a lot of work where I picked two of them, one from Hibbeling and Pollack and one from Bashok and Valentin, where they sort of take a specific problem, find the symmetry group, identify it, and then do the whole computation by hand. And then you have a very long sort of paper of all computations, and then you can put this into an SDP solver, and this is sort of the manual approach, and it's very problem specific. Then there's a few packages already. There's probably more. I just picked the two of them, which work well on specific groups. So in Daniel Borst's package, flag SOS for his flag algebra stuff, he has he has implemented the symmetric group, sort of block Wedderburn, block diagonalization of the commutant for the symmetric group. And then I think I might be wrong, but I think in TSOS, they have special sort of handling for sign symmetries. They're packaged by Ji Wang and Victor Macron. But it might be also integrated in the package that I talk about after this. Then there's another approach, which is you can do this purely numerically, where you take this is Muruta Kanno Kojima, and then another extension with Mayara, where they sort of take a whole matrix star algebra and then try to take a random sort of a generic matrix in there and then diagonalize it and then sort of cluster the eigenvalues and then try to find a good basis from the purely numerical side, which of course doesn't scale that well because you're hard bound by dense linear algebra. And then there is Marek Kaluba's package, which is called symbolic Wedderburn, which works for any finite group, and I think any linear action or unitary action. And they use a purely symbolic approach. So they're exact at every single step until you actually produce your blocks, because then you have to do the matrix multiplication, and this is not very efficient if you want to do it exact, because you have to work in number fields, and so until that step is perfectly exact. And this is also the backend for symmetry reduction in T-source and in sums of squares in the Julia packages. Yeah, so I want to talk a little bit about sort of how to get the block diagonalization very quick. So the basic idea is I won't go into the whole representation theory. This is sort of just the distilled version of the Wedderburn isomorphism, which is you can find, and this is sort of already the matrix version, you can find an isomorphism between your commutant and a direct sum of matrix, of sort of full matrix algebras. And in the matrix, sort of on the level of specific intertwiners, this looks like you find the spaces U, and you apply it to your intertwiner, and then you get just a block diagonalized nice version of it. And we can do this to the level that the blocks are of size multiplicity of the irreducible representation inside the big representation, which is your truncated polynomial ring. So this is the finest possible decomposition that you can do by representation theory. And then we also know exactly how to find this. This is very old. This is written very nicely in Sass book on linear representation theory, where you need to find these primitive idempotents, which are sums over the whole group, where I think you can think, so this G is just the unitary matrix, like, G was a matrix group, so this is just unitary matrix. This is the 1-1 entry, very specifically, of the matrix representation, so of the really matrix form of the irreducible representation. And then you take the inverse, and then you sum this over the whole group. And then and then exactly, if you take this projector and you find an orthonormal basis, then you have already found U for that particular block. So the part of U that makes the block that corresponds to the K irreducible representation. But I mean, already here you can see that if your group is of the order of a few millions, right, which happens very easily, this is not going to be very fun, right? You a priori you would assume that you lose all sparsity that you might have from the group itself or from the irreducible representations. So there is not a lot of hope that this would work in general, or would work well in general. Yeah, exactly. And then, of course, once you've found your basis, you still have to produce the blocks, right? Which is, again, if you're unlucky, which is huge dimensional dense matrix multiplication. So that's also not gonna work usually. And now I want to talk about one special case of groups where this does work very fast. And for this, I have to do like a little bit of representation theory. I want to keep it super shallow. So we say that an irreducible representation is monomial if there is a subgroup and a linear character of that subgroup, so a one-dimensional Arab of that subgroup, that when you induce it up to the whole group, and this is exactly your representation. And if all the Arabs are obtained this way, it means then we just call the whole group monomial. And the cool thing about these representations is that if you write it down, like it's an easy exercise, you write it down, and what you get is, sorry, this should be shifted up. What you get is that for each element G, the matrix form of your irreducible representation is just a diagonal matrix of roots of unity, which are coming exactly from the character, times a permutation matrix. So this is basically as sparse as it gets. And just to sort of say that this is not super uncommon to happen for a group to be all monomial, there's a very large class, I mean, reasonably large class of groups which are called supersolvable groups. They are defined by requiring that they have a chief series, or a series of all normal subgroups, such that each successive quotient is a prime cyclic group. And there's quite a few of them. So I mean, cyclic groups are obviously among them, then abelian groups, but also nilpotent groups, and then between nilpotent and sort of, there's also some interesting groups in there. For instance, the dihedral groups, which are sort of metacyclic groups, are always in there. The affine group of finite prime field is in there. And importantly, for instance, for polynomial optimization, there's also obviously this one is in there, but if you do the semi-direct product between like the C2K, which you can think of like a sign flip group with a supersolvable group, then you're not necessarily supersolvable anymore, but you're still monomial. So there's even space between supersolvable and monomial, but those are also out of it. So it's a reasonable amount of groups that we can already deal with very fast. And the very cool thing is that in 94, Baum and Clausen, who were in, I don't remember. No, I don't remember where they were, but they wrote down an algorithm which computes all the monomial irreducible representations in matrix form, so in full form, in very good complexity, which is almost as good as it gets, like with respect to the non-zero entries that you have in the matrices in the end. This is just order of the group times log order of the group. And this already sort of, in general, is kind of hard to find all the irreducible representations. There's harder algorithms. I think there's a lot of relations between the, like finding all the Arabs of a group with matrix multiplication coefficient. Okay, doesn't matter. There was a paper about this, I think. And now what you can do with monomial groups, or in particular with monomial representations. So let's say you have one, and you have, so you take the subgroup H that it's induced from and the character, and then you say, okay, you assume it's multiplicity mk, and the order of so the image of the character is of order m. So these are sort of the parameters that are important for the complexity analysis. Then evaluating the symmetry adapted basis transform, by which I mean just running u dagger t u, can be done much faster than naive, much faster, in fact. So you only scale with linearly in the size of the representation, which is usually the dimension of your polynomial, of your truncated polynomial ring. And then you're also linearly in the multiplicity. And since you are computing a block of size mk squared, right? So we expect this one to be here somewhere. This is for the dense case, by the way. And the only sort of extra that we have to put is the order of the image of the character, which is a group. Okay, and so this is for the dense case. For the sparse case, you can, you can see similar reductions, and then in the end, you can even go a step further, and you can sort of do the, you can compute the, sort of the subtransform and the Reynolds operator in one. So you start with like a matrix that is not commuting with the action. You apply the Reynolds operator to make it commuting, and then you apply the subtransform, which is a situation that you're often in polynomial optimization, which I will get to in a bit. And you can make this whole operation, you can make it also much faster by just by sort of writing it down. There's nothing deep in there. I think the complexity is wrong. There should be this here, where dk is the dimension or the index of the sub H, plus this part. And yeah, so the idea is you take these primitive idempotents, and then you put in here the diagonal, which is just sort of like a diagonal matrix of characters, and then the permutation. You work it out a little bit, and then you have reduced everything to the subgroup already. So all the like complexity is now sort of logarithmically better. Okay. And now I want to show you that this actually works quite well by a proper experiment. So we take now a family of invariant polynomials. This is a generalized Motzkin family. This I found in a paper by Boss, I think it's CWI. And looks like this. Doesn't really matter. The point is that for k equal 2, you get a scaled version of the Motzkin polynomial, and in fact, the whole family is PSD and not SOS. And there is a nice group of symmetries there. You can see from the plots immediately. So they're all symmetric, so they're always two-variate. They're all symmetric, so you can exchange x and y, which we write into this one. In the dihedral group, this is the reflection part. And then you have these discrete rotation steps that you can do every single k, and this you just write in the rotation part, and then you have a polynomial that is invariant under the dihedral group. And just for, I mean, they have proper zero, so we know the minimum. But so for the numerical experimentation, I use this polynomial because it's kind of easy to understand what's happening, and because the numerical landscape is probably also a bit messy. Oh. Yeah, so we want to minimize this now via the SOS hierarchy. So in the standard setting, I mean, I think many are very familiar with this. We take a vector, so it would be D, but D is the index of the sort of the hierarchy level of all the basis monomials. We need D to be larger equal K plus 1 because our polynomial, or larger equal K, greater equal K. And then the normal SOS relaxation is that you, instead of minimizing polynomial, you maximize an offset T, such that the polynomial minus T is non-negative, which is equivalent, but then you relax it by saying that you also want it to be SOS, which is equivalent to having this Q to be a PSD matrix. And then this equation, it looks nonlinear, but of course, if you write it down, it's just an equation of two vectors. So you get this, and you can find suitable matrices such that for every single exponent, you get one equality constraint like this. And this is the usual SOS hierarchy setting. And in the invariant setting, you just want to sort of change basis first. So you, instead of taking the whole monomial basis, you are allowed to restrict to the basis of the of the invariant ring, which you just get by sort of projecting all the monomials, for instance, which is an inefficient way of doing that, of course, but and then you're also allowed, I mean, then you only have one constraint per basis element of the invariant ring, which is already usually a big reduction. And then what you also can do is instead of, I mean, what you must do, instead of taking these very sparse matrices B alpha, which were sort of the coefficient matching matrices, you now need to average them over the whole group because you need these things here to be equivariant. And then if you do that, you have an SDP, which is totally equivariant. And you can start to block diagonalize it, and then you sort of follow the algorithm. And then here's, for instance, what we get. So I'm comparing with symbolic Wedderburn on the, this is a stupid example because I go up to degree 150, so the hierarchy level 150, which is, totally overkill. But it really shows that this actually scales amazingly. So symbolic Wedderburn has the problem that it's doing, it's as exact as you can be, but for the groups that we are using, we lose all the sparsity because in the end, what symbolic Wedderburn is running is a sparse QR decomposition, which has a very bad worst case complexity. And so this is actually a huge speed up asymptotically, as we would expect from the theory. So that's nice, which works, of course, only for those groups. And then just to look into detail a little bit. So the first steps is where sort of both algorithms analyze the symmetries to find the reducible representations, understand the orbit structure, these kinds of things. And this goes from 10 this is logarithmic, so 10 milliseconds to 10 seconds. It's already huge because the group is tiny. It's just a group of order 20, so Baum-Clausen is just, it's super fast. Then to build the constraints, we save a lot of time because we actually just need to build one very sparse constraint because we do the implicit averaging with the Reynolds operator later. So this goes from almost 12 seconds to almost 700 milliseconds. So that's also very fast. But the biggest win is that we don't have to do sparse QR decomposition. So actually from minutes of scale, we just go down to a few seconds. And that's very good news, I think, for the groups that discover. So super solvable groups and semi-direct products with them. And then, so my conclusion is sort of that symmetry reduction really only scales well to like interesting problems if you have extra structure available. This is why there's so much manual symmetry reduction. But if you write the code carefully and if you really sort of write down everything in like more generic settings for larger families of groups, you can still do a lot. I mean, this works for all the super solvable groups and monomial groups really. And so this is currently in development. There's not a lot of documentation right now. If you want to have a look, feel free to scan the QR code. Yeah, thank you. The blocks, I mean, they are like, so the ambient space dimension, and let's say in this case, I think it's like 50,000, and the blocks are all around like 100 to 1,000. So because, I mean, the group is very small in comparison to the space. I mean, it's still a huge SCP, but the point is that, there's much, so if you have a bigger group, then you get much smaller SDPs because you have a lot of more high dimensional irreps, right? In this case, this was like a toy example, just to see the scaling in an example that is not super technical, and this was the easiest that I could come up with. No, this is not a toy example for an SDP server. Agreed, yeah. Any other question? Excuse me? Jonas over there has potentially a way. We should talk about this at some point here, because I'm not sure. So we talked about it a little bit in the past few days. I think there's a lot of error accumulation over all those steps. And then I think that the hope that you can actually extract good minimizers from this, I think it's kind of low, but we have to try. I have never tried. Maybe should.
Any other questions? Maybe I can ask you, how would you recommend for someone who's not so good with symmetry? How can you spot in your problem that if you have such a super solid
Okay, good question. Like, so there's a lot of classes that are kind of easy to spot. Like, for instance, a dihedral action. Like, I mean, an abelian action is very easy to spot, which is for sure super solvable. Dihedral actions are kind of easy to spot. Usually when you have metacyclic actions, which means a semi-direct product of two cyclic groups, which you would get, for instance, also for the affine group of the finite prime field, which is translations and multiplications. Those are also kind of easy to spot. For nilpotent groups in general, it's a bit harder.
Maybe try
Yes, one way, I mean, one sort of algorithmic way would be to, if you have like a parametric problem, like take a small instance, run it through GAP, and then take that out. Like GAP doesn't have these algorithms, right? But I mean, this can classify for sure a lot of groups. I mean, all of small ones. Yeah. Yes. Yes. I mean, so the super solvable ones are a special case of monomial groups, but this is just sort of what I have right now. There is, for instance, also the same people, Baum, Clausen, they also have very concrete algorithm for solvable groups, which is not as fast because there's a lot of primitive irreducible representations there, which means you have sort of density in the matrix forms of the representations. And so this is going to be less efficient, but this is the best case possible, I think, for symmetry reduction, or the sort of the best compromise between general and fast. Yeah, the super solvable groups in particular.
Okay, there's no more questions. Let's thank Luca again.